Okay, I guess we're live. Andrea, can you check if it's working properly? And
Sorry, can you hear me now? I can, yeah.
it's working?
Yes, I can see you in the link.
Okay, great. All right. Hi, everyone. I am Nafisa, and I am joining you as a Girls in Quantum team member from Bangladesh. With me, I have another one of our Girls in Quantum team members, Andrea from Romania. So to kick off day two of our Kivolution event, it's my great pleasure to introduce someone whose work quite literally operates at the quantum level of cool. I'm talking about Professor Paul Griffin from the University of Strathclyde, who has mastered the art of making atoms dance and tell time. So Professor Griffin's team works on technologies that sound like they're straight out of science fiction, to be honest. We have chip scale atomic clocks, magnetometers that can detect um, brain waves, and ultra cold atoms that hover just billions of a degree above absolute zero. I hope I got all of those right. And his career has taken him from Durham University to Georgia Tech, and from NIST in the US to being a Royal Society of Edinburgh Research Fellow in the UK. But what makes him a perfect speaker for us today is that he's known not only for pushing quantum science forward, but for making it understandable and exciting to us. He even teaches a university course on communicating physics and training the next generation of science communicators to have their ideas tested and their metaphors stretched. So whether he's wrangling atoms or explaining quantum tech in a way that even your grand could get behind. Professor Griffin is proof that physics can be as powerful as it is poetic. So please join me in welcoming Professor Paul Griffin. Professor, the stage is yours.
Thank you very much for that overly kind introduction. So yes, my name is Paul Griffin. I'm at the University of Strathclyde, which is a university in Scotland, and was very well described there. My research interests are primarily in taking quantum technology and using it for applications. So I'm not going to talk very much about that today. I'm going to talk more about an overview. I think the challenge I was given was to talk about the quantum technology landscape. And I should have started sharing. So my background is in physics, is applied physics, which is this intersection between, sorry, I'm not allowed to share at the moment. Should have checked that for. So it's the intersect about quantum is cool, right? Hopefully anyone who's watching this believes that already. But when we have interesting science, can we use it to advance society? That's the real thing we're trying to push for. And so given that quantum is now more than 100 years old, which is why we're in the International Year of Quantum, why is it that it's still stuck in universities, and why is it that it hasn't gone into the mainstream? If I can, one of the reasons I think quantum has a strange reputation, and I think the reputation is undeserved as being hard. And I'm disappointed always with this, because I prefer the word challenging to hard, if possible. Challenging in the sense of, if you're going climbing, would you like to go on a nice flat gentle walk? Some of the times when you want to push yourself, you try something that's higher and harder. And so quantum, like any other subject, like any other job people have, all jobs are hard. And I think the problem with quantum is that it was mythologized by some leaders of the field, particularly Albert Einstein, as being ununderstandable, and he didn't like it, is the short way around it. I don't think it is that difficult. It's no more difficult than any other subject out there. I just think it's very interesting and challenging. So I'm going to talk about the quantum technology landscapes. I think the important thing to dig into here is the people. The people are what drive all this. So this is a photograph, or a series of photographs that are running, not the most recent in all of them because we still have COVID pictures, but it's about the people that we work with and the teams we work with. And hopefully you see in a lot of these pictures, it's people who are smiling, engaged, they're doing something that they find inspiring. And that is my hope, is that if you can study a subject that you find fascinating, it makes your job a whole lot easier down the line. And hopefully gives new opportunities. And that's where I'm going to try and lead through this project. Start off with a quiz. We'll come back to this later, but as the idea here I'm going to ask is, which of these rely on quantum physics? We've got semiconductors, the basis of the computer I'm using, the chips that are transmitting information over the network, the sat-nav in your car, which uses GPS or other technologies. You've got brain scanners that use this technology called magnetic resonance imaging, or lasers. Right? Which of those are quantum physics? Some of those are everyday. Your remote control in your television is going to have a lot of semiconductors in it. If you check out at a supermarket using a self-checkout machine, that's most likely using lasers to read the barcode. Where's the quantum in all that? We'll come back to. Over time, I've asked a lot of people, my own family, and always the general public, what they think about quantum. And the words that come up on a word cloud are going to be weird, it's going to be spooky action at a distance, mysterious, and various versions of incomprehensible, which is that it's not understandable by the likes of you or me. That's the general gist that often comes forward. And I don't like that. I think it is very understandable if someone puts effort into it, in the same way that learning a new language is understandable if someone puts effort into it. Go back for a bit of history. This person here is Nicholson. So he's one of the people who was involved in showing that the ether didn't exist even, sorry, the other way around. So one of the problems with special relativity was, why is the speed of light this constant? And it couldn't possibly be, given that light traveled through this mysterious background. So he was an excellent experimental physics who proved some of the background, or provided the data that set the foundation for special relativity. And he said, quite a long quote here, I won't go through it, but it's shortened in some degree, but it's probable that most of the grand underlying principles have been firmly established. The future truths of physical sciences are to be looked for in a 6th decimal place. TLDR, basically there's nothing to be left in physics other than measuring more accurately, as it's often paraphrased. And this was in 1894, about 10 years before the start of quantum mechanics, before special relativity actually come around. This is when he was doing his measurements at this point. He wasn't trying to prove anything at that stage. And we know now ourselves that a huge amount of the world has changed since the late 19th century, late 1800s. We have quantum mechanics, we have special relativity, we have artificial intelligence, a whole bunch of other techniques that are coming through. But our understanding of physics in particular has fundamentally changed. At this time, at the late 1800s, classical physics broke things down into different areas. There were waves, like waves in a guitar string, waves in water, and we things that are particles. These Highland cows that we find everywhere in Scotland, the Eiffel Tower, Lego, football, these are definitely particle-like things. What do we mean by that? So if you go into a physics class, we describe waves, or things that have waves show features such as interference. So this picture at the bottom is showing water where 2 stones have been dropped. We're getting waves that propagate out, that's fine. But these interesting features that happen around these areas are that the waves start to interfere with each other. At certain points, I get 2 waves come together and they add. And at certain points, I get 2 waves that come together and they subtract. They cancel each other out destructively. And that's wave-like behavior, which leads to things like rainbows. It leads to things like interference, these lovely colors you see on water, very thin layers of, and duck's feathers as well. Particles, on the other point, like this bouncing tennis ball, are described by having a position. I can say where the particle is. These snapshots are showing where the tennis ball is, and it has a trajectory, or it has a way it moves, which we can see by the bouncing in it. And in classical physics, I could describe the motion of this tennis ball. If I knew where it was and where it was moving, I could predict how it would move forever forward. With waves, I can predict how they're going to interfere with each other, and we're going to see some interesting physics now. And they did not cross each other. There's a nice line in between. And quantum mechanics came around in the early 1900s, and it started showing weird things. So on the right-hand side, this pile of dots are experimental data, effectively, showing what happens if single electrons went through a wave-like experiment. So on the left-hand side, we've called what's Young's double slits. It's a famous experiment that proved that light is a wave, which is that a wave is incident on this screen on the left-hand side, and the screen has got 2 slits, one at this position here and one at this position here, and the waves propagate through. And as the waves propagate through, we see these bands where there's light and dark. That is because the wave from one slit and the other slit start to talk to each other, start to interfere. And as we move further and further away from the screen, we can see that these waves form into beams, which we call an interference pattern. So this picture on the left-hand side is a simulation showing optical fields. The right-hand side here, the very far right, is showing at this position at the far right-hand side, what does that wave look like? We've got periods of high intensity and we've got areas of low intensity. And In between, we have what we see if we put particles. Electrons most definitely are particles. When we pass them through the same experiment, we see that the electrons interfere. The electrons behave like waves if we prepare them in particular waves. And this came into this idea that light is both a particle and a wave. This picture here is that we have this problem that we need to start thinking about is, what is it? Is light a wave? Is it a particle? Is an electron a wave, a particle? And it created interesting problems about quantum mechanics. And this is one of the first confusions that came around about, which is this is not like classical physics. A Highland cow suddenly doesn't tunnel or doesn't interfere with another Highland cow. So this person, Albert Einstein, coming back to, was one of the fathers of atomic quantum mechanics, but it's also one of the people who held it back over time, which I'll get into. At the time, he said, this wave-particle duality is that we have this difficulty. The difficulty is that we have two pictures of reality from our everyday world around us, but when we get to the quantum regime, neither of them work, right? The wave picture doesn't work by itself because light can be a particle and a wave, and the electrons can also be particle and waves. And he said, what we need to do is figure out some new way of combining these together. And so Einstein was one of the drivers of this field very early on. And I'm not going to mythologize people all the way through. I'm just going to bring out that as someone familiar. I'm going to label it here. This is a badly cropped version of the medal that Einstein won his Nobel Prize for. Einstein, a lot of people think, won it for his Nobel Prize for E equals mc squared. He most definitely wasn't. He won a Nobel Prize for this equation on here, which says that the energy of a particle is quantized. It's going to be a relation of the frequency of the wave multiplied by this constant called Planck's constant. This is the evidence or the background that actually proved that quantum mechanics is correct. And in the idea showed that light has to become particles, has to have a particle-like behavior. It has to exist as what we now call quanta, which is the origin of quantum mechanics, which is that energy comes in chunks. When we think about the world at the fundamental level, the level of electrons, atoms, photons, we need to think about it in a different way. We come up with this field called quantum physics, which combines different techniques from wave physics and from particle physics, and it describes how these fundamental particles interact with each other. And that was the idea, is that let's just take away our preconceptions and just use techniques we already have and bring them together. So when we talk about quantum, it doesn't mean mysterious, it doesn't mean some kind of hocus pocus. It really means we're talking about the rules that control the tiniest particles in the universe. We're talking about atoms, electrons, and photons, and we talk about them at the very low energy scales, which is different than what we're used to. So, I am made of hundreds of billions and zillions and quadrillions of atoms. That's why I don't behave like a quantum device, because I'm made of lots and lots of atoms. But at the individual level, we need to worry about it. In quantum physics, then leads to things like entanglement, which I'll come on to in a little bit, which is that in a classical picture, if I take a coin and I flip it, I can get heads or tails. It will be one or the other, unless it lands on the edge, which is very unlikely. But a quantum coin, when you flip it, until we look at it, is both heads and tails. And it has a nature of including in that one. So this idea of superposition. And if I flip two coins, I can have the two coins be related so that if one measures head, the other one, no matter where it is in the universe, will measure the opposite, it will measure tails. And this comes back into the kind of mystical part behind it, but it comes out naturally from fairly simple equations. And what I'm saying in that sense is that if we follow and work through the mathematics behind this, the results come out, and we can do experiments to show these aren't just made up. And this is what leads on to the weird, spooky kind of nature aspects. But what I'm going to say is that there's experiments have been done over 100 years that show this is how nature behaves on a scale that we're just not familiar with, the very, very, very small. So this is a famous picture called the Solvay Conference from 1927. There's 29 people pictured on here, of them 17 won Nobel Prizes. So this was a really exciting time in physics. The kind of people that are on here are Erwin Schrödinger. Schrödinger was one of the people involved in quantum mechanics, and like many other people, started to dislike it very quickly. When you came to this thing about when I flip a coin, it's both head and tails at the same time. And the way he described it as being absolutely nonsense was he said, well, that's equivalent to, imagine if I had a box, and inside this box I put a cat and an atom, and the atom could be in one state or the other, until I measure what's going to happen to that atom. Well, let's just imagine if that atom decays, it causes a vial of poison to break apart, right? And so if that vial of poison breaks apart, it's going to kill the cat, right? So is that saying if I don't know if the atom is up or down, that means I don't know if the poison has been broken, which means I don't know if the cat's alive or dead. That's nonsense, right? And it turns out Schrödinger cat, we don't do these experiments with cats, we do these with atoms and photons. We can make Schrödinger cat states all the time. this guy Pauli, who's on here. Pauli was one of the people who talked about the fact that electrons have got these weird behavior that I cannot put two electrons in the same place at the same time. Heisenberg, going back onto all these kind of weird ideas, Heisenberg was the person who came up with the idea that we can't know where a particle is and how fast it's moving at the same time. And the reason why that is confusing is because I said a particle, but a wave I'm quite happy with. If you think about a wave propagating across water, the wave isn't at a particular point in time. The wave is spread out over. And so these natures that Schrodinger, Pauli, and Heisenberg were talking about was just the fact that we still had to figure out the language we were using. So the other people in here, Niels Bohr was a person who started accepting that the maths might be correct. And Bohr was saying, what happens if we start applying it to the atom, which is some level is made up of protons and neutrons in the center and electrons around the outside. And he came up with some predictions, and the predictions matched the theory extremely well. And this is where we come into what the idea of science is going to be, is I make a prediction, I do a test, and if it matches. And we have to get rid of our biases, and we have to get rid of our preconceptions. Einstein, who's in the center for a reason, was this big famous person at the time. And around this time, Einstein started to fall out of love with quantum mechanics because it started revealing some kind of things that just felt a bit metaphysical. By metaphysical means that it didn't relate to the realities he understood. And of course, we have Marie Skłodowska-Curie, who won 2 Nobel Prizes, the only people who are here who won both. She was one of the people who discovered radioactivity, came up with the term radioactivity, discovered new elements, invented radiotherapy, and transformed chemistry, physics, and medicine as we know it. With this organization here, if you think of these people, and including the people who didn't win Nobel Prizes, there were some very, very clever people who got very excited and advanced this field very, very quickly. So back to this question I asked beforehand, if you thought about it, which of these rely on quantum physics, you're probably not going to be surprised that I'm going to say answer is actually E, all of the above. The semiconductors we use are entirely based on, are designed around the principles of quantum mechanics. What happens when I get crystals of silicon and allow electrons to move through those when there's certain things added? GPS I will come back to in a little bit, but GPS relies on atomic clocks that are floating around in space, which is just cool, I think. Magnetic resonance imaging relies on the fact that we can interact with hydrogen atoms that are within the water molecules within your brain. And that allows, by looking at these kind of pictures, measuring where there's lots of hydrogen, measuring where then the blood flow is going to. And lasers are a fundamentally quantum system. That's what happens when atoms and light interact. And we get these really cool effects called stimulated emission, which means that one photon makes an exact copy of itself. And there's these really interesting features. Again, these all exist, and you probably have hopefully use some of these and not all of these, but they already affect our life every single day, which is cool. I'm an experimental atomic physicist, so I like using atoms. And reason why I like using atoms as a quantum system is because they are made up of fundamental particles. So in this periodic table, there's a huge range we could use, but the kind of atoms we use are the ones on the left-hand side of the periodic table. So if you have any background in chemistry, you'll remember then that these are formed by atoms that have 1 electron in the outer shell. So, and some of these atoms, such as rubidium, will have 37 electrons. 36 of those will be nicely paired up in closed shells, and there'll be 1 on the outside, which is active, we can use for interactions. And the physics we use then is how we interact with those atoms, move those electrons around at different levels. Why an atom then afterwards? Just because I can do it. The reason is that because if these things are going to be useful, for example, like an atomic clock, one of the areas of research, I would like to make lots of clocks. And one of the things we propose in physics is that the laws of physics are the same no matter where you are in the universe. So if I take, for example, this number of protons and neutrons and number of electrons, and I do it here on Earth, or I do it on the other side of the universe, I should see the exact same behavior. Not should, we expect it to be exactly the same. And that allows now to do very interesting tests. And then there's a third point about atoms, is that atoms are sensitive to things. I mean, in the sense of gravity, if I take an atom and I drop it, it falls under the force of gravity, the exact same as this bouncy ball that I have. That means an atom is now sensitive to gravity. Can I use quantum mechanics to measure the force of gravity? And yes, we can. Some of the most precise measurements of gravity are using atomic physics at this point. So a little background in this area I'm going to say is, which we're going to dig into a little bit, is just hopefully you'll accept or trust me when I say atoms have energy levels. What this means is that atoms can have particular kind of states. So we're going to model a picture of the atom as being protons and neutrons in the center as a nucleus. We can imagine this, if you want to think of it, as a picture of the solar system. And then we can have the electron can exist only at different orbits. And if we think of this back to the solar system, we'll say, for reasons we don't need to go into at this point, the electron can exist at the orbit of Mercury, Venus, Earth, Mars, and so on. And the energy the atom has depends on how far away the electron is from the nucleus. So Mercury is tightly bound into the sun by gravity. If we go out to Uranus, it's less tightly bound. And so the Mercury, we're going to say in that system, has got a different energy than in the solar system analog, which falls apart very quickly. But let's just use it as a model for a moment. So if the electron is further away, it has a higher energy in the system, we're going to say. It's more likely to escape. So in this picture I have here, I've got the same protons and neutrons in the center, and the electron, if it's close in, has got a low energy. If it's far away, it's got a high energy. And because of the wave nature of the electrons, we can come up and say that the electron can only exist in these particular orbitals, can't exist in between. This is the quantization of energy within the atom. And for the atom to go between a low energy state and a high energy state, it has to emit or absorb light. And so when an atom absorbs light, that emission or absorption tells us something about the energy levels of the atoms. It allows us to say the difference in energy between those two different states. It also means that particular atoms will have particular fingerprints, which then also allow us to do spectroscopy and learn what's going on in the atomic systems. So for example, here's a picture of what a hydrogen spectrum would look like. And these hydrogen spectra, the reason I show them more, these were experiments, again, that were done in the 1800s, particularly in Scandinavia, where people were looking at the sun, which you should never do, but they were looking at the sun and measuring the fact that the sun spectrum had bits missing, which is what we're looking here at the top. And so we got an absorption spectrum, which is if I shine light through hydrogen, or the bottom, which is an emission spectrum, if I heat hydrogen up and measure the lines it emits. The presence of these lines come about directly from the fact that hydrogen has particular energy levels. And so this picture at the bottom of the emission spectrum is if I make hydrogen excited, put it up to some higher energy level, what are the colors of light that are emitted? And so we have this equation that Einstein won the Nobel Prize for, which says that the color or frequency of light tells us about the energy it has. Red, which has got a low frequency, has got a particular energy. And as we go to the blue end of the spectrum, we get more and more energy and higher in frequency. So these transitions here, which are called things like the Lyman alpha and Balmer lines and so on, the names aren't important, were the basis that inspired Niels Bohr taking all this other physics that was coming together to say, if I look at the spectrum of hydrogen, it is quantized. It emits energy only at particular levels. How can I bring this emerging tech and theories coming out and combine them together to figure out the nature of atoms? And this feature is one of the things that we use then every day in our kind of labs. So how do we use this kind of things? We use lasers. And so the idea in this one is that a laser is going to be a source of monochromatic light, meaning light of just one very particular color. So we shine a laser beam onto a system, you might inherently think it's going to do something bad. It's going to cause explosions. And so lasers are very frequently used for cutting in steel, for example, but lasers are also used for precision measurement. So that hydrogen atom that really wants to emit or absorb light at particular colors, if I can get a laser that emits at those particular colors, I can interact with the hydrogen in a very interesting way, or carbon, or whatever atom is going to be. The atom we like to use is an atom called rubidium. And the reason we like to use rubidium is the fact that the lasers are the exact same lasers that are in a laser printer at home. So the lasers themselves are just freely available. They're standard technology. And this is important because some of the work we want to do, if we think it's useful, we'd like to make lots of them. And so I would like to have, rather than have to build a Death Star every time I did an experiment, I would just be able to like to go and buy this commercial off the shelf. So this is an experiment of one of our old style labs of what we do. So I'm deliberately showing it because it's kind of gee whizzy. We'll move on to other areas later. What drives these kind of experiments? We have lots of electronics, we have lots of lasers, and we have lots of vacuum systems. The vacuum systems are there to protect the atoms. So the air around us, we've got nitrogen molecules that are whipping around at hundreds of meters a second. We want to make sure when I interact with this atom, create some delicate quantum state that it isn't hit by a nitrogen molecule or oxygen or wherever it may be. And in the corner here, we have Billy, one of our former PhD students, who ran this whole experiment wearing laser goggles because he's been very good and safe. But with this experiment on here, we could do interesting things. What kind of things could we do? We could take lasers and shine them on atoms. So what you see here, this glowing ball, is not atoms that are burning hot. These are atoms that we have cooled down to fractions of a degree above absolute zero. And by fractions of a degree, these atoms are about a millionth of a degree above absolute zero. And so this is one of the things that came out in the late 1800s was the fact that there is a lowest energy scale on temperature. The idea I'm going to use here is that if you think of water and the jiggling motion that's in water, we're going to talk about energy and more importantly, temperature as being a measure of how much kinetic energy, how much motion particles have. So if I think of a picture of water, if I have a glass of water and I heat it up, the molecules jiggle more and more, and the more jiggling they have, at some point they gain enough energy that they can escape as steam. If I cool the atoms down instead, and they take energy away, they're going to jiggle less and less. And at some point, the jiggling is going to get low enough that the atoms, then molecules, even more importantly, are going to bind together to form a crystal called ice, or a solid called ice. But the jiggling is still happening at that point. And so you can calculate from some equations, again, going back onto it, we know the energy is given by something like that relates to the velocity, a half mv squared, if you've come across this before. If I keep reducing this jiggling energy, there becomes a velocity go to zero, and there's a temperature associated with that. The temperature is very, very, very cold. So the temperature in Celsius is minus 273.15 degrees. So far colder than outer space, far colder than anything we know in nature. But these atoms, by shining lasers onto them, we can take all that jiggling energy away. We can take that jiggling energy away such that they're now cooled down to 0.5 zeros and 1 degrees above absolute zero. And interesting things happen in these areas. What kind of interesting things happen? Well, the interesting thing that happen is that we can start engaging with quantum mechanics, right? So this is when I bring people into my labs and we're like, we've got this laser on here, and what we use them instead for, rather than making dangerous cutting things, we use them to create the coldest places in the universe and then do precision measurements within the systems. And those precision measurements come about from we're measuring on this very, very low energy scale. When I talk about very low energy scale, we're measuring in the fractions, the lowest scales you can think about, let's put it that way, rather than start giving more numbers. So why would I use atoms? The picture I talked before about atoms is that we have protons and neutrons in the center, let's call it the nucleus, and we've got different energy levels. I've got a low energy and a high energy level. I can think of those as being like a switch. Let's just say the electron is the lower energy level. I'll call that switch being on or off, whichever you prefer. Let's just go on because it makes my slides easier. And then if I put in electron in the other energy level, that will correspond to a switch being off. And if anyone here is a computer scientist, well, a switch has been on and off, I can just call ones and zeros. This makes a very nice bit in computational physics. Quantum mechanics, though, says, and does, allows us to create interesting states of these electrons, that I can make the electron be in both energy levels at the same time, as long as I don't as long as I don't ask the atom what state it's in, it can exist in a superposition. What that means then we got to think about is, well, is my switch on or off? And quantum mechanics, what it says is that it's both on and off at the same time, or the cat is alive and dead, right? And we do not work with cats, we work with quantum particles. But this is a superposition state. The atom is both in the excited state and the ground state. It is both a 1 and a 0. It is both on and off at the same time. The cat is both alive and dead. And that isn't just a curiosity. We can use this feature to do interesting physics. We can use it to explore, is quantum mechanics correct? The answer is yes. We can use it to also then do measurements on systems. And for example, one of the areas talked about, as introduced, we can make very accurate clocks. We can make very accurate sonic magnetometers. We can do very accurate measurements of gravity. And so back to come on to this part here is why study atoms, and why do I study atoms? Other people study other systems, and I'll touch on those later, is because we can now examine the nature of quantum phenomena. We can create these superposition states, what we call Schrodinger cat states, and we still use that term because it is just evocative. It is kind of like, I don't know, for me it's inspiring. There may be other terms that one might use. And this is perhaps one of the problems with quantum mechanics, is that we have a lingo associated which may come across as gatekeeping, but we have these states. I can make an atom be in two different levels. I can also make an atom be in two different places at the same time for very short periods of time and in a very delicate experiment. We do things called entanglement. And this is coming back to where I think one of the problems with quantum mechanics came from, was this picture on the right-hand side is taken from the front page of the New York Times. I've never been on the front page of the New York Times, but Einstein was every now and again. And Einstein was on the front page because he attacked quantum theory. And the title at the time was Scientist, being Einstein, and his two colleagues, that was Podolsky and Rosen, found that it is not complete even though it is correct, with quotes around complete and even though it's correct. And that's a very fancy way of saying, I don't like it. It might be right, but I do not like it. It's not complete even though it is correct. That very much feels like what a toddler would say to their parent when they're told to go to bed. And this is where the problem, I think, with quantum comes out. If it's on the front page of the New York Times that the smartest man in the world doesn't like quantum mechanics, well then what chance do the rest of us have? And I will tell you the chances that it's actually a fascinating subject. There's loads of wonderful things we can do. And the wonderful things are still going on. It's not just in the 1800s, as the Nobel Prize 3 years ago was given for using quantum entanglement, the fact that I can have particles at different sites in different places where their results of measuring one would immediately affect the measurement or would immediately correspond to a measurement on the other one. I can make a quantum state that is separated over space. And it leads to very interesting topics, as we'll come on very briefly to. One of the things we can look at is wave-particle duality. And the idea in wave-particle duality is, I started beforehand, we have things like particles, which have definitely a position, like this little ball, and it's got a vector. And this arrow pointing off is going to tell me which way it wants to move. But waves start to become delocalized. They start to spread over space. And this is the only equation I have on my slides, I promise you. But we have a picture saying as I go lower and lower and lower in temperature, so the arrow pointing right is higher temperature, what we see is that I'm going to introduce this picture that particles become more like waves. As they become lower in energy, they become more like waves. And these equations at the top came from someone called Louis de Broglie. We started when quantum mechanics first was coming around, was basically saying light is both a particle and a wave. He was like, well, why can't particles both be waves and particles, like an electron? And he has an equation on here which says this Planck's constant, it's just a number. Mass is just the mass of the particle. We got the thing KB, and this is the thing here T. So if you ignore everything else in the equation, it basically says the wavelength of a particle, how wave-like a particle is, depends on the temperature with this square root term. Let's just ignore that for a second. I've got an equation which says the waveness depends on 1 divided by the temperature. And that means, even if you're not very comfortable with maths, as I make the temperature smaller and smaller, that wave nature gets bigger and bigger. What kind of temperatures do we need to get down to in order to make this wave nature very important? Well, it turns out to about 1/1000th of a degree above absolute zero. And so in the experiment, that picture I showed you where we have about 1 billion atoms at 1/1000th of a degree above absolute zero, there the wavelength of the particles is comparable to the wavelength of the light that we use. And as we cool down even cooler, we can go down into the nanokelvin regime, billionths of a degree of absolute zero. We enter this new state of matter called a Bose-Einstein condensate. And so this picture we show here on the left-hand side is the one I showed earlier. On the right-hand side is some results I took with one of my colleagues, Aidan Arnold, who was leading this work, was where we take 2 clouds of atoms and we drop them. And as we drop the atoms, we get this image that looks like this. It's interference. We take 2 atoms, we add them together, and at some points we get 4 atoms appearing. And we take 2 atoms, we add them together, and we get 0 atoms. So this, what we're seeing here is a 3-dimensional picture of an interference pattern. We get a peak where atoms gather, and we get a trough where there's no atoms in between. This is exactly not like how matter behaves. This isn't how the Highland cow interacts. But when we get matter and cool it down to very low energy scales, we can start to measure this wave-particle duality. This result is only explainable if rubidium is a wave, but also a particle at the same time. Right? And we've had lots of people email us and say, I've got a new theory. It doesn't work that way, I'm afraid. I'm very happy to listen to all those theories, but the simplest explanation really comes down to quantum mechanics is correct. These waves are not just a curiosity. I love this image because we spent a lot of time working on it with some very excellent PhD students driving it, and with some very nice theory in the background. What we can use this for is now we can make extremely accurate measurements. I'll just rotate that image around so they look the same. We can make extremely accurate measurements of gravity. We can make extremely accurate measurements of magnetic fields. We can measure interesting things. I think that is just very cool. It's like, so there's a physics. I would like to do cool research. I would like to train up very good scientists. Can we also go out and measure gravity more accurately? Why would we like to measure gravity more accurately? Some of your speakers that will be here during later in the week have worked in these areas beforehand, but the idea is going to be, if I'm trying to find water underground, water has got a different density than rock. So if I made a gravity map of the ground, you can find underground structures, like for example, wells of water. You can use it for a whole range of applications of taking the fact that the Earth doesn't have the same acceleration due to gravity everywhere because there are things underneath the ground that could be interesting. And that's cool, I think. Hopefully you think that, well, I think everything I'm talking about today is cool because I've selected all these things, but hopefully you do think. Back to quantum technologies, right? I was talking about some things I specifically care about. The idea in quantum technologies is that there's a lot of argument what these definitions are, but what quantum technologies are technologies that exploit atomic physics. They let us do things that we couldn't have done beforehand. So it's really a field of engineering / physics, right? It is taking this stuff out of the lab and doing interesting work with it. So what we're trying to say is take practical applications that have disruptive potential. And by disruptive, we mean change the way that we try and do measurements, change the way that we look at nature, do interesting areas. And but the point is, we're going to control single particles, be they atoms, be they photons, spins, defects, superconducting qubits, wherever it may be. And can we use them for sensing, computation, and aspects? So quantum technologies is, you could say, started back when people first started coming up with quantum mechanics. This is a thing called an n-gram. Basically, you go onto the web, you can see how often terms appear over time. So about the 1990s, this is looking up the term quantum technologies. Quantum technology comes out the same way. There's a very brief bump around 1990, which is when cold atom physics first came about. People started using laser cooling to get to these levels, and people started developing atomic clocks. And then about the year 2000, it kicked off. And in the last 5-10 years, this field of quantum technologies has exploded. And that's because of its disruptive capabilities. It isn't that it is boffins in a lab, a term I absolutely hate. It is that it's really moving into industry. It's moving into really interesting applications like quantum computing, like quantum key distribution cryptography. There are entire fields, and we do like this picture of the Schrodinger cat. It's cute. We can stick these, imagine that these cats are doing experiments themselves on its case. There's a whole field and whole journals that are coming up about this area. And again, I promise it's not just an academic curiosity. It's not just people like me in labs. It really is moving out to society. So there's a bit of background here. On the left-hand side is a picture of the first transistor. So this was using a bulk piece of semiconductor and large soldering aspects. And this was just showing that semiconductors could exist. And what semiconductors were doing were basically replacing valves. These were using thermionic emission. We had plates inside a vacuum chamber, and you could bombard electrons back and forth. And the first semiconductors were not really clear what one could use them. Some of the first applications were things like hearing aids, where it was such an awkward device, only someone who had transformative capabilities to their life would start to use it. But now we're getting to the point for semiconductors where they're ubiquitous, by which I mean they're everywhere in the world at this point. They're everywhere in modern society at this point. The cameras that I'm using, the phones around us, the thing that measures the water level in your washing machine are using semiconductors. This picture I showed of Billy in the lab beforehand, that is where we're in the transition at the moment. Can we go from having these systems that are built up over years and can do really, what we call hero experiments, which work after lots and lots of effort, to the point that we can start making these scalable? These could be now at some point like a computer chip that you could buy that would just be in every sensor that you have, that is going to be in your mobile phone or wherever else. And that's what the revolution that we're in at the moment is, this translation that is happening. So the first quantum revolution, it was about understanding atoms and subatomic particles, things inside the protons and neutrons as well, and understanding the physics behind it. And it took a long time to get onto the second quantum revolution, which is that we understood and we started harnessing these technologies very well. Things like lasers were invented, and our techniques of controlling them became better and better, to now using them as technologies, things that can do something we couldn't have done beforehand. And the kind of range of applications that are coming into, and these are real applications that people are using, are civil engineering, which is things like buildings. Can we use better gravity sensors to figure out where buildings should go? Telecommunications, which is, there's a whole range, but just the fiber optics that are beaming my talking down the road. Healthcare, this idea of MRI, magnetic resonance imaging, and a whole different areas. And finance, and one being particularly a strange one, you mightn't think about it, but the stock exchange in the UK has regulations that it has to use quantum mechanics in their timing. They need to use atomic time stamping on all the transactions that are used. And that's there to provide security. It's to stop espionage, and to stop people manipulating the stock market. So quantum mechanics is so trusted, it is used to control the stock exchanges at this point. This revolution has been going on for about 10 years, and it's still going. And we're at an interesting point in that curve I showed that we're still shooting upwards in the time. There is a lot of hype associated with quantum mechanics. I'll come on to some of it in a little bit, but an awful lot of it is actually will come to fruition. And the kind of areas we're thinking about, if we can make better quantum clocks, but that means, I mentioned that GPS works in the fact that there are clocks in space. So in order for your GPS system to work, I'm going to skip ahead a couple of slides. If I can find my couple of slides. The way GPS works is that there are satellites in space that have really accurate clocks. These clocks broadcast the time. And so how can I use that to figure out where I am? Well, some clocks are further away than others. And so the speed of light is very, very fast, 299,700 kilometers per second. But it travels about 1 foot, 30 centimeters in 1 nanosecond. So the fact that these satellites are different distances away from me means if I bring up a GPS receiver, I will record the signals at different times. And these clocks are so accurate that I'm so precise that I can measure the difference in time of arrival of these different signals. So if I have 3 different satellites and I know the time myself, I can position myself to being where I am in Glasgow at this point, position myself to about 10 meters, which is amazing. And that entirely relies on the fact that there's quantum mechanics, quantum physics, quantum technologies floating in space. And as an example, me and my cats want to figure out, we do like cats, we broadcast, they emit at the exact same time, but the time of arrival is different for both. And so that's the idea that we can use of better quantum clocks allow us to give ourselves our positioning, our locations more and more accurately. As mentioned before, and we can make magnetic sensors that can measure brain activity. Navigation means that we can actually start without having to use GPS to locate. Secure quantum communications. Quantum enhanced imaging means things as crazy as can you image through a wall? And there are applications and people working this across the world. And getting onto things like quantum computers. At some point, it becomes overwhelming. Quantum, 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 right? We don't just stick quantum in front of everything. Like there are a lot of quantum things out there, right? So if you go to the supermarket, you'll find quantum toilet paper, quantum washing up liquid, quantum dentistry, whatever it's going to be. It very much is a buzzword. And some of that buzzword comes about because sometimes scientists get very excited and really believe that it's going to be transformative and maybe get a bit carried away. I'm going to pull that back and say 3 areas, I think, the highlight areas of quantum technologies that are really important. Quantum sensing and imaging, which is where I do most of my work. There's quantum communication and quantum computing. I'll start with the latter. So quantum computing is a particularly highlighted area. And so Bill Phillips won the Nobel Prize for one of the people who invented laser cooling and perfected it in 1997. The idea in quantum computers has been more powerful than classical computers. He made the point that a computer we have today is based on the same principles as an abacus. That thing you had as a kid where you can slide beads from side to side to learn how to count, maybe even in decimals. And his point was quantum computers are as different from today's computers as today's computers are from an abacus. They just work on different principles. But there's a lot of interest in things like, can we have effects in understanding protein folding, which would affect disease discovery? Can we look at drug discovery? Can you solve problems which are very difficult, such as things like how do you solve traffic management? When I say traffic management is difficult, it is very, very complicated. Physically, computationally, the whole shebang. It's just an interesting system. And because quantum mechanics work in different ways, there's a lot of hope that we can start solving problems which are related to, such as energy distribution, which is going to be extremely important for green energy in the future. So quantum computing uses a wide range of hardware. I keep talking about atoms, so I'll come back to it again, but you can use atoms, you can use ions, superconductors, photons, molecules, different areas. Back on to Erwin Schrödinger, who didn't like quantum mechanics a bit. His point was, at this time when he was a very influential person in this field, but was also saying in the 50s was that we are no more likely to do experiments with single atoms, single particles, than we are to raise an ichthyosaur in the zoo. Ichthyosaurs being dinosaurs, right? This is a picture of an ichthyosaur from the Natural History Museum in London. These are pictures from the lab that's adjacent to mine, one of my colleagues, John Pritchard, where he traps single atoms in tweezers. And he makes arrays of 225 qubits that can talk to each other. A quantum computer that isn't hypothetical, it is addressing interesting problems in this area. And this is 5 years out of date now, is that quantum computing is when I say on the cusp of a commercial breakthrough, quantum computing is very much a commercial reality. There's lots of people working in this area for very interesting problems. Quantum communication tries to address the problem is that we want to send secure information. If you talk to your bank or you talk to your doctor or you're transferring any information, you want to have it transmitted between, we historically use the terms Alice and Bob. Can you transmit information without an eavesdropper finding out about it? And the laws of quantum mechanics, using this thing called the no cloning theorem, basically says that we can provably transmit information that can't be intercepted. And he uses these ideas of entanglement and superposition and this idea of Schrödinger's cat again to show that this can happen. The interest in this area is that the amount of hacking that's going on. My own country, Ireland, is talking about 4 years ago, the health service was taken down at a huge cost as well because of the insecurity of our networks, or more importantly, the ability to hack secure networks is getting stronger and stronger. And we need to have secure communication for just the fact that I really do care that my health data is protected, or my banking information is protected, or the nuclear secrets are protected, wherever it may be. And so quantum key distribution, this idea works around, is now a reality in the sense that quantum keys are distributed over space. There are satellites in space that are sending single photons containing secure information down to Earth. There's a huge area of research in this. Quantum sensing, as I mentioned, is brain scanners, imaging around corners, and so on. And I'm not going to talk as much about that because I think I've already said enough about what kind of things we work on. So maybe jumping ahead, given time is available. Does anyone believe all this other than, the converts to this cult of quantum already? These are some data come from an organization called Querca, who look at the world international landscape. So these are from 3 years ago. I couldn't find any more information. And it looks at the money that governments across the world are putting into these areas. So if you want to pick a big country like China, it's $15 billion. I have no concept of what 15 billion is. It's so large. The European Union, the United Kingdom, all these different countries, but you're getting smaller countries, including Ireland, Denmark, all across the world, that are putting money into these areas. Why? Because one, the idea that this can change the way that we work, can change the be better for society is very important. The second thing is they can create highly paid, skilled jobs, which inherently means more taxes back to the country. So it's one of those kind of fruitful environments that investing now can have very large rewards later. And that creates interesting topics that people can work in. Sorry, I'm going to skip over that part. So when we think about, does anybody care about these kind of aspects? I'm going to look at the particular example of the UK where I am based. So we have had 10 years, we're in the 11th year of the UK National Quantum Technology Programs. And this has been based around different aspects. We've used hubs, which are centers of excellence. And in the third phase even of the quantum technology landscape, we have now got 5 hubs, of 2 of which I'm involved in, which are the UK hub for quantum enabled position, navigation and timing. We're making better clocks, we're making enhanced LiDAR, we're making better inertial sensors. In the QSIT hub, it is looking at distributed networks. What happens when I combine quantum gravity detectors with quantum magnetometers? QBiomed is looking at, can we use these principles, focus on particularly on medical problems and looking at interesting aspects in there. There is quantum computing, and then there's the quantum networks, quantum key distribution. And so this is putting focused effort with hundreds of scientists, hundreds of companies working together. And as an example of some of the companies that we work with, I mean, you might never have heard of Strathlight beforehand, but these are the kind of companies that we work with on developing technologies, including the likes of Google and so like there's a huge area of this work being transformative. So why should you care? What does this mean for you? No graphics this time, because I think these answers speak for themselves. Societally, this is transformative. If even a fraction of what has been promised comes true, and it is already coming through, there are better brain scanners out there at the moment that use less power and are more accurate based on the devices that we're developing across this community. They make better healthcare, make better cybersecurity, and make advances in climate science, and ... I mean, that is that we are at the point where we just don't know what this could mean necessarily. For anyone watching, I would say careers is, given the fact that I would say having a job you care about makes your life more interesting, right? It makes makes your job less of a job, but also hopefully leads to progression afterwards. So it's physics and engineers, but there's a whole area in software development. There's an interesting area in ethics. What does it mean to have control of quantum secured information? How should you deal with it? There's a whole aspect related to law that is now going to become interesting about these superposition states. What does it mean when information is distributed over different areas? Again, there's a whole interesting area that can lead on to. And one thing I'll come on to is that quantum is not going to take over. We're not going to lose classical computers. Quantum are going to augment, not replace the classical world. So this picture down here is one of our colleagues, Joe Cotter, who makes inertial sensors. He puts these onto boats and can measure a very accurate way that sensors are moving around. His quantum sensor, he combines it with classical sensors to get the best of both worlds. So we have these kind of plots that we use where, again, you can have, where we've got a quantum inertial sensor is better in some features. What we say is here, at longer times, the quantum sensor outperforms the classical sensor. And by combining both of those together, we can basically get the best of both worlds. And that's what we're proposing here. And what people across the world are proposing is we're not trying to, the revolution isn't to wipe everything away, it's to make it better. So coming to the end, this picture, I think I've used it many times, but I think it's fascinating. This is the idea of the triumph of science, that science can change the way things work. So Alexander Graham Bell, a Scot, invented a telephone in patent for a telephone was in 1876. And then thousands and thousands of scientists, engineers, and workers worked for a very long time to try and make this useful, right? So his first phone call was to a person in the room next door. And then in 40 years later, a phone call was placed going from Washington to California, transcontinental in the US. And at this time, Woodrow Wilson, who was the president of the US, described it as, it appeals to the imagination to talk across the continent, right? This wonderful technology came out and it was a nice idea. It was good for people to play around with. And at some point, it connected people across continents and then even further across the world to communicate. And communication is a fantastic thing. It drives science, it drives different areas. And I would say this is the point that we are at right now. We have developed these wonderful technologies. We have thousands of people working in these areas, driving these industries, making very interesting applications and environments that we can work in. And the applications are starting to come to fruition. As I mentioned, computing, cryptography, sensing, these are really coming real devices at this point. And the excitement would be, I mean, Niels Bohr pretty much was famous for saying whether he did or didn't, we should never predict anything, especially about the future. But I do know it's going to be exciting, whatever comes next. So I would like to very much thank the girls into quantum for inviting me to give a talk about this word, but I really think it's if this 100 years of quantum, which is the International Year of Quantum Science and Technology, is that should be asking questions. What does this mean to us? What can it do for me? And everyone should be asking this because it's our world. Okay, so thank you very much.
Thank you, Professor Paul, for such an amazing keynote. Like, even we as moderators got to learn a lot, and I'm hoping that the participants really could. They had a lot of good takeaways. So I'm going to take some questions from the people who are watching the live stream. We have one question. So it's about um, why do some scientists feel unsure or uneasy about the idea that a quantum state is something real, like a physical thing?
I would say observation is a key thing in science. This is I liked finding out things myself. So one of the things I liked about going to university and studying was that you can do, for me as an experimentalist, I really like going into labs and measuring things. So when you measure yourself that the acceleration due to gravity is 9.8 meters per second squared, that's just cool. As my kind of personality. And so actually seeing it is very difficult for these kind of quantum states. It is the measurement of showing that this kind of Schrodinger cat state requires some abstraction, by which I mean is we don't go in and see the cat alive and dead. We see it alive or dead, the atom being in one state or the other, and then we repeat the measurements and then we come up with some models. And like I showed with this wave particle duality with our atoms, we have a model that matches. And I think that may be one of the things is that some of the training we have, particularly in high schools, but also just in life around us, is that some people and naturally just have different ways of evidence of wanting to see things. That's just my own feeling. I'd be interested to hear if anyone has other thoughts.
So another question, I think it's about the secure communication part. So some people say that quantum key distribution might not be useful in the long run. So why do they think like that? And is it really true?
I can point a lot of colleagues who would get very annoyed about that. And maybe it's an argument of where it goes. So there are some problems with quantum key distribution. So to be very clear, we're organizing a meeting here in Strathclyde the next 3 days, which is going to be about quantum networks in space. So we're fully bought into this area. But so some of the things that come up about quantum key distribution is that at some level I can send this absolutely secure quantum information and then I'll store it on my computer and there's nothing to stop some bad person breaking in and looking at my computer. You buy a better lock. The problem we have with the communication networks at the moment is when you and I are talking on here, there's nothing to stop every network server in between to sample the data and put it back in again, right? So it gets rid of that part of the chain. The other problem that comes into is that these quantum states are very fragile. So if I send these photons into an optical fiber, the optical fiber is not perfect. After transmitting of tens of kilometers, if it may be even 100 kilometers, this quantum state gets damaged. And so that's one of the concerns is fine within Scotland, maybe even within the UK, we can have these quantum networks. But if I want to talk to Singapore, for example, how is that going to work? And the idea that we have, and lots of people have, is you go up, you go into space, you shine the quantum information through the atmosphere, it goes to a satellite, and then the satellite can beam it across. And this is already used. So there are networks there's a mission called the MISIUS mission, which is the Chinese government have, and they have had quantum communications between Austria and China beforehand. So there are all these things have got lots of problems. I'm very clear. If they were solved, it would be kind of boring. So whenever we have meetings, it's like, but what about? And that's the thing that we like is that maybe instead we could try something else.
Yeah. Another person wrote that quantum computing is taking longer than going to the moon, isn't it?
Yes, quantum computing is in a very interesting phase. We're at there's a lot of interesting things happening and the results may not have been seen. There are reasons why this may be. One is there are a lot of companies developing it now and companies have reasons not to reveal all their information. So in the same way that I do not know how Google's algorithms work at some level, I know some of them, but not others. There's going to be proprietary, which is being protected information. But quantum computing is showing progress. There are algorithms that work. There are things which are using analog quantum computing, digital quantum computing. There are problems being solved. Have we solved, and this comes back to maybe where the hype is the problem. In the early day, there were statements that quantum computing would cure cancer. And I was like, that's a very bold statement. That is not happening anytime soon. In no more way that a classical computer cured cancer. It might do, but it's very unlikely. What is happening is quantum computers are addressing very specific problems that can then be used as part of this fight against these aspects. They're very complicated problems, and sometimes easy answers skip over those points.
Right. Thank you for the wonderful answers. I hope the participants understood what Professor Paul is trying to say here. Personally, Professor Paul, I think I really liked the way you used Star Wars reference in the slides. That was really interesting to explain the portion about lasers. I think the spooky action at a distance, that particular topic is like it's really interesting how like Einstein, he didn't really agree with the fact that quantum mechanics is complete, but he is the one who laid out the whole foundations of quantum mechanics. And it's nice that we stopped thinking about the weirdness of quantum mechanics and really started to adapt it like a feature, not like a bug. So it's your entire talk was very enlightening for the participants, I'm hoping, and as well as for us moderators. Andrea, do you have anything to say?
First of all, thank you again, Professor Paul, for this amazing session. I had just a question. What skills do you think are most useful for someone who wants to work in quantum technology one day?
Very good question. I think in any research field, my opinion is enthusiasm. That's the important thing, right? There's a desire to learn. So I think there's a paper I like to give to a lot of students I have here, which is the importance of not knowing, which is about the fact we again, going back to the challenge things. I'm not going to climb a mountain no one has ever climbed before, but some people are driven by that kind of way. So we address difficult problems, and so that requires a kind of a characteristic which is doggedness, by which I mean take on a problem and maybe accept the fact that it will take a long time to solve, but we're going to work towards it. And it is that enthusiasm. So there's times experiments or theory don't work, and you say is like, well, let's go back onto it, right? You go, you have a cup of coffee, you take a few days away and get a holiday, and you come back in again. And if that enthusiasm is there, going back onto the point about work, I think that is really what drives everything. There's this 99% perspiration, 1% inspiration. There absolutely needs to be ideas behind it. But I would say this idea that you have to be clever to do quantum is a problem, because most proper people don't think of themselves as being clever, right? So most people are like, oh, that's not me. And I think that's a huge issue in here. It's like anybody can do this stuff. In the same way anybody could study CRISPR in biology, or different aspects in this one. If you're driven and you're motivated in that part, you definitely can make contributions. So that's all I would say, is interest and drive.
Okay, thank you. And also, what inspired you to study quantum physics? What sparked your interest in that?
I don't really know. I liked reading as a kid, and I remember reading about, I can tell you I was very interested in being an astronaut at one point, and then something happened in between. I don't know. But this is why one of the things I like about the work we do at the moment is that we do work with the European Space Agency, and there's a little part in my head that says if I could go back to 7-year-old Paul and tell him that he would be doing stuff with them, that would be kind of cool. Also, when I talk to my family and I tell them I'm working on quantum, like, yeah, whatever. Then I say I work with Space Agency, they get excited. So that in between. But the bit that really got me was in labs in university, and getting to play with these kind of things and building interferometers, and that click moment as an experimentalist. And I'm sure someone who's more into data science or computation or whatever it may be will have a different click moment for them. But that was what it was for me.
Thank you.
All right, I guess we can stop the live session now. We have another session right after this one. It's on Introduction to Quantum Computing with Qiskit. So we will be seeing you guys in the next session. Thank you so much.
Thank you.
Thank you. Bye-bye.